Section 12.7 is all about forced oscillations. Our objectives here are to adjust the simple harmonic motion equation to include a driving force, and also explain the concept of resonance and how it's affected by damping. Now, forced oscillations are ones where you are applying some sort of outside force to do work on the system. Energy is going to be transferred to the system or input into the system, and that applied force would be in the direction of the motion. Imagine that you have maybe a kid on a swing, and as that kid sits on that swing, you know that eventually their motion is going to get slower and slower, and they're eventually going to stop, right? They would be a damped oscillator. But if you wanted the kid to keep swinging, then you could give the kid a push, right? This is what we mean by a forced oscillation, that you are giving this thing some sort of a push, exerting a force on it to keep the motion going. And you'd find that the amplitude of this motion would remain constant if the amount of energy that you input for every cycle was equal to the energy lost from that resistive force. So if you push the kid with just the right amount of force, they will continue to swing with the exact same amplitude over and over and over again as they go back and forth. You would be inputting the exact same amount of energy that you are losing to those resistive forces in that case. Now, since the force varies periodically, you kind of give a push, wait a second, give a push, you have this general equation for that force, where F would be equal to F naught sine of omega t. Omega is the angular frequency of that driving force. It's generally different from omega naught, which again is that natural frequency of the oscillator. And F naught would just be a constant. That means that our equation for the motion of this oscillator would have our input force, the resistive force, and the restoring force all being set equal to an MA. When that driving force begins to act on an initially stationary object, the amplitude will begin to increase, and after a sufficient amount of time, the input energy would equal the energy lost, and the object would be in a steady state with a constant amplitude. And now we could write this as our oscillatory motion, or a simple harmonic motion equation, where again it would fit the pattern of A cosine omega t plus phi, but the A here would be this big guy right there, where you'd have F naught over M all over the square root of omega squared minus omega naught squared, that quantity squared, plus B omega over M, that quantity squared. And again, just to remind you, omega naught is equal to K over M. Now, let's take a look at that amplitude equation one more time. Remember, we said it was F naught over M all over the square root of omega squared minus omega naught squared, that quantity squared, plus B omega over M, that quantity squared. What I want you to notice is that the equation for A, we see that A is actually constant for a given driving force, meaning that there is no t in this equation anywhere. It doesn't depend on time like it did in a damped oscillator. Again, we have a constant amplitude based on this driving force that sort of matches or inputs the energy that you're losing. Now, for small damping, A would actually become really large when the frequency of the driving force is near the natural frequency of the oscillator. Basically, what we're saying here is if omega naught, if this omega here were to approach omega naught or be about equal to omega naught, this on the bottom would become smaller and smaller, right? Because if you actually got to your omega or your driving angular frequency equaling omega naught or the natural frequency of the object, then this whole term would cancel out to a zero. You'd be dividing by a smaller value, and A would start getting bigger, essentially. Now, omega naught, again, is that natural frequency. You would now get this dramatic increase in A as your driving frequency approached the natural frequency. This is what we call resonance, where, again, this omega naught would actually be considered the resonance frequency. Now, notice from the graph here how large A can grow. In fact, it grows exponentially as omega approaches omega naught. If you start pushing this oscillator at a frequency near the natural frequency of the object or the material that this is made out of, this is going to grow exponentially for the amplitude of this motion. Now we can see here that A is actually going to grow more with less damping. So we can see that the undamped oscillator actually grows infinitely much, but a lightly damped oscillator would peak at this omega naught value, and a heavily damped oscillator would also peak at this omega naught value, just not peak as high. So the amplitude wouldn't be as large with the more damping that you put in there. So more damping, you still see a peak happening at omega naught, but that peak isn't as high. With less damping, you see the peak getting bigger and bigger. And in fact, if you had something that was completely undamped, if there was no B value at all resisting the motion of this oscillator, then your A value is actually going to approach an infinitely large number when you approach the natural frequency omega naught. Again, this is the idea of resonance. In real life, there's always some amount of damping, but you can look for situations where that damping is low and then see amazingly high amplitudes of the motion when you approach resonance. We'll talk more about resonance when we come back to class and show you some examples of that.